we have a cis dash 3 dash formol dash 4 dash cyclohexene carbonitrile. There's an E there, sorry. Cyclohexene E. So whenever we're doing it, we don't want two constants touching. So that's why we put the E there. Cyclohexene carbonitrile. Are there any questions on this one? Yeah. Yes. Otherwise, it'd just be a nitrile if it was in a chain. Yes, I should be recording. Oh, wait, am I recording? I think I started. Yes, I am. Okay. Anything else? Anyone else? All right. On to the second one. So this time we have an amide. So this structure, this OR and then NR. This is or NH. This is called an amide. So we're going to be naming it from the parent structure, which is, yeah, so from there. So this is going to be our first carbon, which is connected to the oxygen. So this is going to be our first carbon. 4, 5, 6, 7, 8. So we have an 8-carbon chain, and then off of the nitrogen, we have two 4-carbon chains. And so because of that, we have technically we have 3 substituents. We have 2 substituents off the nitrogen, and then 1 substituent off of carbon 5. So our first course of action is going to be to name our parent chain. So for the parent, we're going to start with it's an octane. So we're going to start with octane, and then remember that we have an amide. So what we're going to do, instead of writing octane, we're going to write octan and then amide after. So that is going to be our parent chain. You don't have to clarify that it's on carbon 1 because that's the carbon that we start at on amides. So it's just octanamide. And then onto substituents. So we have 2 nitrogen subs and then 1 sub on carbon 5. So the sub on carbon 5, because it's just the benzene ring, this is going to be called a phenyl group, 5-phenyl. And then the subs on the nitrogen, they are classified by the N. So we're going to have N, N dash dibutyl. So after this, we don't have any stereochemistry, so now all we have to do is put it together. So remember, when doing this, we just have to go by alphabetical order. So the butyl is going to come before the phenyl. So we're going to start N, N dash dibutyl dash 5 dash phenyl octanamide. And that will be the naming for the structure. Are there any questions on this one? Yeah. No, there's not. It's just my writing is low-key. If you put a substantial space, maybe. Like if it's like if we go to for the next one, maybe I'll like try to show like what a substantial space would look like. But I think just for that, I don't think you would count that wrong, or like count any points off for that. Anyone else? All right.
Sure that if there's no dash, you don't have a space.
It depends on the. We'll see on the next one.
Yeah.
No worries. Okay, so on to the next one. For this naming, we have an ester. So our ester is going to be our main group that we're going to look at for the parent chain. So the way esters are named is actually pretty interesting. So we have two groups on either side of the ester. So one side is the carbon side and one side is the oxygen side. So whenever we're naming these, both of these are going to be classified as substituents. So the way it'll be written, well, not substituents, I guess. This is going to be considered like the parent chain because it's going to be going after the this side that has the oxygen attached to it, right? So on this side, well, I'll just name the left side as the parent and then the right side as the sub. So parent. So for our parent chain, we have an 3-oxo butanoate. That's so butane and then O8 for the ester naming. So because it's 4 carbon and then ester, so butan O8. That was a big space. And then on the right side we have a substituent. This is going to be a 1-cyano. So the nitro group, when it's a substituent, is going to be called a cyano group. So cyanopropyl. And then now that we have everything, we don't have any substituents for this. So to put it all together, we're going to start with the cyanopropyl, 1-cyanopropyl. But for your first thought might be to put a dash here. But because we're naming an ester, we're going to leave a space in between and just start with 3-oxobutanoate. And that would be actually the correct naming for this. The 1-cyanopropyl 3-oxobutanoate with the space in between rather than a dash. Are there any questions on that? About naming or anything? All right. Sounds good. So onto the facts section. This one, the first facts question is asking us to place the compounds in order of increasing reactivity with H3O+. So in this one, we want to see how stable the leaving group is going to be, right? So whenever we reacted with H3O+, this bond would be cleaved on all three of these. And then you're going to essentially look at all three of these and then see which one has the best which one is the most stable. So we're going to look for stability. So more stable leaving group. So to start, what we're going to do, we're going to start by whenever we make these leave, these are all going to be O-. So we have O- all the way. And we're only gonna look at this first part. So we'll look at this part and see how stable the leaving group would be. So for the first one, we have a electron donating group, this CH3 by induction. So it's gonna very weakly move electron density towards the benzene ring. So it's pushing some electron density towards it, so it's going to be slightly destabilizing the negative charge. Because the more stable is going to be, the more this charge is going to be pulled toward the ring. So we want a group that's going to pull the charge rather than push it back into the ring, right? So for our second one, we have something that's going to be pulling charge away from the ring. This is an electron withdrawing group, right? So this is going to be pulling charge away from the ring, and it's also going to be pulling charge away from the oxygen. So this oxygen is going to have a weaker negative charge, and because it has a weaker negative charge, it's going to be more stable, right? And lastly, we have an electron donating group, which is going to be feeding electron density in towards the benzene ring through resonance, because it has lone pairs, so it can do it by resonance. So because of this is going to be a stronger donating group. So this is a stronger donating group, and so it would lead to the O- charge being being higher, so it'd be less stable, right? So because it's less stable, it would have the least reactivity. So this is going to be our least reactive one, and because our first one is going to be slightly destabilizing, it's not going to be as stable as the second one, because the second one is going to be pulling more electron density, and so it's going to be a smaller charge on the oxygen. So this is going to be our number 3, and our first one is going to be number 2. Are there any questions on that one? No? Okay, we'll move on. So the next one is asking us to place the compounds in order of increasing acidity. So our first course of action, what we can do is to remove this hydrogen on this carboxylic acid on all 3 of these, because it's pretty much going to be similar to how we did the first one, like probably the same. So we have an O- on all of them, and so on this one, we see that we have 3 groups. 2 are electron donating groups, so these NHs are going to be electron donating groups, and this amide is going to be an electron withdrawing group, because this is pulling electron density toward it. So because of that, we know from the start that we want something that's going to be more stable, and so it has the smallest negative charge. So because this is going to be pulling a negative charge toward it, this is going to be because this, for the electron withdrawing group, for the third, for the third, then this is going to be our most acidic molecule. Again, my bad, guys. And then now we have to decide between the first structure and the second structure being acidic. So our first structure is going to be withdrawing electron density. It's going to be giving electron density towards, donating electron density towards the CO2, CO2 minus. So what that's going to do on both structures is that it's going to cause the O- charge to be a little bit higher. So between them, we can also have the charge propagated the other way. So in this case, in the middle, the charge could also go to the O, and this is going to be another electron withdrawing group, but it's going to be slightly pulling some of the charge that would rather be going to the O2 minus into the double bond O. And so because of that, this is going to be a weaker electron donating group than the first one. So this is a stronger. And because it's a stronger electron donating group, it's going to be the least acidic, and this is going to have the middle acidity. Are there any questions on that one? All right. So moving on. Place the compounds in order of the hydrate formed in NaOH. So in this, we're going to be looking at the charge on this ketone carbon. So we're going to look at how the charge is moved around on this one and see which one is going to be the most stable. So whenever we do this, we know that this charge is going to be delta positive on all 3 of these. So we have a partially positive charge in all 3 of the structures. So in this one, and on the third structure, we don't have anything pulling the charge or adding to it. So it's just going to be, let's just call it like net neutral, partially positive. But in the other two, we have not electron withdrawing groups, because technically this is an electron donating group, but this oxygen is delta negative. So what it would also do, even though it's an electron donating group, it would still pull some electron density, causing this to be even more partially positive, right? And so this OH would also do something similar, but it's slightly further away. So it can't be as strong as so the delta positive isn't going to be as strong as it would be in this center one. So because our delta positive charge is going to be strongest in the center one, is going to be the most unstable. So it's going to want to react more, right? And so that's going to make it form more hydrate in NaOH. So it's going to be it's going to have the most hydrate formed. And then our second one, because this is like net zero, this is going to this is going to slightly bring it, this is going to slightly cause it to be more delta positive. So now this one is going to be number 2. And so our final one is going to be number 1, the last, which is going to leave the delta positive charge. Are there any questions on that one? Probably could have explained that better, but. Yeah, so this oxygen in the center, it's partially negative, right? So even though it's an electron donating group, because it's partially negative, it's going to pull some electron density towards it. And so because of that, it's going to cause the ketone, or not the ketone, is going to cause the ketone's carbon to become even more positive. So it's going to pull some electron density from that carbon. And so that's going to make it more positive, more reactive. So, yeah. Anyone else? All right, sounds good. All right, place the compounds in order of increasing acidity. So this next one, what we're going to have to do is look at the alpha hydrogen. So this hydrogen, whenever we have acidity in an anhydride structure, not anhydride, but a, forgetting the name, but it doesn't matter. In this kind of structure with like two carboxyl groups, we look at the center carbon, and this has a hydrogen attached to it. And whenever we're doing acidity, we're going to be removing that hydrogen from this. So we'll look at this with the minus charge, the same way we looked at the other ones with the minus charge. So for the first one, this minus charge, this is going to be this is going to be pulled both ways, right? So all of these are pulling the negative charge towards the oxygens. It's just that for this one, we have 2 electron donating groups that are going to prevent some of that from going, and this side has no electron donating groups, which would cause the charge to be, not pulled as much. So in this case, if we look at the oxygen, this is going to donate some electron density over here. So this carbon right here that's attached to this double bond oxygen is not going to want the minus charge as much, because it has access to the minus charge that the oxygen is providing, right? And the same goes, it's the same logic goes here. So this nitrogen is going to donate some electron density, and so it's going to need less electron density from the minus charge to pull it, right? So because of that, it's going to be slightly less stable. So whenever we have, it's going to be less stable because, it's going to be less stable because the minus charge is going to be higher, right? Because let's just say in this like control case, we have the minus charge is like split halfway, right? Now, let's say that this still like pulls like half the charge, like 0.5, but this one might start pulling 0.25. So there's going to be 0.25 still on the charge, right? So it's like it goes by that concept that the charge still is going to have more charge on it if it's pulled less. So that's going to cause it to be less stable. So the more the charge is pulled, the more stable it's going to be. So in both of these cases, the charge is pulled in a way that, in the first two cases, the charge is pulled in a way that the charge moves, but it's not going to move as much as it would in the third case. So our third case is going to be our most stable structure. So number 3. And then now to debate between oxygen and nitrogen, we know that oxygen is a more electronegative atom, and so it wants to oxygen is a more electronegative atom, so it wants to keep its electrons more. So what's gonna essentially this is going to be stronger for the electron density, and so because of that is going to be more stable than the nitrogen would, if that makes sense. Are there any questions on this one? Yeah. Right. Okay. So the oxygen, whenever it has an electron withdrawing group, so the oxygen is already partially negative, right? So what's going to happen is that the partially negative is also going to slightly pull some electron density. And so because of that, because it's more partially negative, it's going to be, how do you say? It's going to be causing this to be more partially positive, right? So this this ketone where this double bond is going to be more partially positive because it's also, even though it's a donating group, it's also pulling some electron density. So between the oxygen and the nitrogen, the oxygen is going to want it more, right? And so that delta positive is going to be higher, and so it's going to pull more electron density. So it's going to cause the minus charge to be slightly lower. Yeah.
I've seen problems where like
Between stable leaving group.
if it's sometimes like a reaction point. Like yesterday,
2017.
if there's like a reaction happening, then once it splits it, and that's when you look at the this one, we're just looking at like
Yeah. Just straight acidity.
I'll try to find it. Okay. In that case, I would oxygen. Yeah. If it was like a O minus versus a B minus. Okay.
Anyone else? Sorry. All right. So for the last one, it's asking if the compound would be decarboxylated in H3O plus at 180 degrees Celsius. So whenever we have decarboxylation of H3O plus at 180 degrees Celsius, we need an alpha beta beta keto ester. Beta keto acid. So in this one, what that essentially means is that if we start at the carboxylic acid, so this is the carbon of the carboxylic acid. If we start here, we go alpha, beta, and then if there's a carboxyl group here, this is going to be decarboxylated, right? So in this case, our carboxyl group is going to be on alpha, beta, and this is going to be our gamma carbon. So this is going to be our third carbon, and so because of that, this is not going to be decarboxylated. So for the answer for the first one is going to be no. For the second one, we start with this carbon again. So if we go alpha beta again, alpha beta, we see we have a carboxyl group here. So this is going to be decarboxylated. So we're going to do that for the third one as well. We're going to start with this one. We can start on either one, to be honest, but we'll just start on this one. So alpha and then beta right here. And this is the beta that has the C double bond O OET. And that is going to be decarboxylated. So also yes. Are there any questions on that one? Then no? Yeah. So whenever we look at this, if we go either way, because I went the first from the other carbon, the first one, I'll go by this one. So we want a beta keto ester, which means that we want on the beta position, we want there to be the double bond, a keto, or a keto acid, sorry. We want there to be a C double bond O, a carboxyl group. So whenever we go at the alpha position, we don't have anything, but we want it at the beta anyway. So if we go with the beta, this carbon doesn't have any double bond O to it, right? But the third one, alpha, beta, and then gamma does. And because we're only looking at the beta position, this is going to be a no. Does that make sense? Any other questions on that one? All right. So onto the reaction section. So this is going to be our first reaction. So our first reaction, we have a carboxylic acid that's going to be treated with COCl2. Remember, COCl2 just changes the carboxylic acid into a acyl halide. So an acid halide, I guess. So this is going to be, for our first step, is going to change this OH to a Cl. So we're going to have O and then Cl. Right. And then for our second step, this is the, I'm blanking. Not Grignard, but it had a name. I'm completely blanking. I'm sorry. Gilman's, yes, Gilman's. Yeah, Gilman's reagent. Thank you. And what this does, even though it says CH, it has two of the substituents, it's only going to add one of them. So that's what makes it special. If this was a Grignard reaction, because it's an acid halide, it would actually attack twice because the Cl is a good leaving group, and it would leave it to be an alcohol. But because we have Gilman's, it's going to be it's only going to attack once, and it's going to take the place of the chloride. So for our second step, we're going to have the double bond O bonded to a CH2 bonded to the benzene ring. And that's only going to attack once, and we're going to keep it as a ketone. And lastly, this is going to be the Wittig reaction. So in the Wittig reaction, this double bond O, one thing I like to do with the Wittig, I just change this to double bond O because that tells me like how the bond is going to be. So for example, this double bond with the CH double bond P is going to be the same as this double bond to this C double bond O. So essentially what we're going to have is just this entire thing being replaced with the entire right here minus the O. So to draw that out, we're going to have this double bond. We're going to, and then we're going to have our H. And this is just going to be this CH. So this is the, sorry, let me draw that actually. So this is going to be our C bonded to the H. And then right over here to the other side, we're going to have our benzene ring. And that is going to be our final answer. Yeah. In this case, I think what she would test on if you're doing stereochemistry for this, just don't put the biggest groups beside each other. So in this, I'm just putting the big benzene groups on opposite to each other so that there's less steric hindrance. Any other questions on that? I'm not sure if you would get points off, but just it's a good thing to do. Just all right. So it's tragic. So for our next one, we have an aldehyde, and it's adding quite a group onto it, and so this is going to be just something to memorize. So this is going to be done during Stork synthesis. So what Stork synthesis does is that it creates an enamine, and then from there we can add a group like this. So our first step is going to use a secondary amine. So our first step is a secondary amine. So NCH3 CH3 NH CH3 CH3 / H plus. So we always need the H plus, but we can use any secondary amine that we need to. So in this, I'm just using NCH3 CH3. You can also use, I think in the lecture notes, she used N like this. If you guys remember that / H plus, I think that was in the lecture notes. But you can use either. It just has to be a secondary amine. So our first step is going to be to substitute that aldehyde with the amine. So this is going to be bonded to the N now, and it's going to be an enamine. So this double bond is going to be created, right? So our second step is going to be to have add our group. So we're going to add the group CH2C, the alkane group. So CH2CH, or I guess we're going to put a bromine on it. So Br-CH2CH double bond CHCH3. And what that's going to do, that this bromine is going to attack this carbon, causing this to move over here and have a double bond, creating an imine with an IMINE. So we're going to have an imine after this product. So this is going to be after step 2. And okay. And then we have our CH2CH double bond CHCH3. And now to get rid of the nitro group, which has a positive charge, not the nitro, amine group, which has a positive charge on it, we're just going to use H3O plus. So our third step is just going to be H3O plus, and that is going to give us our aldehyde back. So are there any questions on that one? Yeah. This is just, you just have to remember to do that. For this one is kind of just memorization. Like, we'll go into the other one where we have the 1,2-diol. And for that one, we're going to have 2 carbonyl groups. And this one, we only had 1 carbonyl group, so we used Stork synthesis. Yeah. Yeah. Because sorry. This is a hydrogen right here. I kept drawing it, but it's just a hydrogen. Yeah. I mean, in this case, yeah, it would be enamine to imine. I'm trying to think of a case where it wouldn't be. I'm pretty sure just because also one way to also know if it's Stork is because this is on a beta position. So we have the alpha and then the beta position. So this is on the beta position, so we would want it to be like we would want it to attack that way. So that's why we use the Stork synthesis, so that we had this alkene. So we had this alkene right here, so that the BR could attack that. That makes sense. Oh yeah. What was that? Oh shoot, yeah, alpha. My bad. Yes, alpha. You're right. My bad. Any other questions? Yeah. Yeah. Uh-huh. So if we were gonna use that, the thing is, all we would have whenever we use that is just something like this, right? And so because of that, there's not really a place for our reaction to take place, right? Because we want it to go onto this carbon right here, but there's not anything that's making it react there, right? NaOET minus. Yeah, to get the minus charge onto it, because I don't think that would work uh, for the diol, because not diol, but for the ethylene, because what was the reason? Because usually it does it. The minus charge is in between it. Because whenever we have that NaOET, the group looks like this usually, right? And so the minus charge would go in between. So if we had it over here, there's no double bonds on either of these oxygens. Like it's bonded twice, but there's no like actual double bonds. And for carbons in between, it has two carbons in between. Yes.
I would say one hit for this one is a little bit trickier since you're not doing reagents. If there's two carbonyls,
Yeah.
so in the one that we looked at yesterday, we had a ketone and an aldehyde. In that case, that's a pretty big hit for the acetyl production group, especially because aldehydes and ketones are differently reactive. Aldehydes are more reactive. So then that one would react with the acetyl, and then you can do stuff with the ketone. For this one, kind of what Hamza mentioned, if you do an alpha-alkylation, so you add an alkyl group of whatever our group, the alpha position, that's a hit for Stork.
Yeah. Like, sorry, for cutting you off, but we're also gonna go over like the other one, but like if you can see, like, we would use the ethylene glycol, but the ethylene diol, but it would have like if you can see, it has the the aldehyde on both sides, but this ketone was replaced with an OH, and then it had a different group attached to that. So like it's like all about where the alkylation would occur, I guess. So are there any other questions on this number 2? Yeah. Beta keto beta keto esters, or I think beta keto ester. Yeah. Sorry. And usually it would be with ethanol. Yeah. Anyone else? All right. Moving on. So this is our third reaction. So from this reaction, we have CH3NH2. What this is going to do is we have an anhydride right now. We have a cyclic anhydride, and so what this would do is it would attack one of the carbonyl carbons. And so let's say if it attacks this one, this would cause this O to have a minus charge, and then this minus charge would resonate back down, and it would kick this O off, and it would cause, because it's a good leaving group. So what the product for that looks like is going to be a 5 carbon chain. So 1, 2, 3, 4, 5. On our first carbon, we have the double bond O. We have our double bond O, and that's going to be attached to an O minus. And then for our second one, well, it's OH. Like, it would get protonated. And for our second one, we would have our for our carbon 5, we'd have another double bond O, but this time it would be an amide. So we would have an NHCH3. So because it's a single subbed, here, let me write that a little bit better. NHCH3. So because it's a single subbed amine, this would come and attack, and it would become a single subbed amide. And so going on, our second step, this is Fischer esterification. So whenever we have Fischer esterification, we're gonna have the alcohol attack the carboxylic acid, and what that's gonna do is gonna cause the carboxylic acid to become an ester with this group that it's attached to. So our second step is going to be to have this same thing, and then our O, and then we're going to have this oxygen, the same OH, but it's going to become an ester, so it's going to be OCH3. And then our third step, LiAlH4, then H3O+. So this is a reducing agent, and what this is going to cause is it's going to cause the ester to become an alcohol because it's a strong reducing agent, and it's also going to attack the amide. And what it's going to do to the amide is going to cause the amide to become an amine. And what that's going to essentially do is just going to get rid of the double bond O, and the ester is just going to, instead of having the double bond O, OCH3, it's just going to become OH. So we're going to have our 5 carbon molecule. Wow, that was bad. 5 carbon molecule. And then on one of them, we're going to have our NCH3 bond to an H, NHCH3. And then on our second one, we have our OH. Or wait, no, that's OH, like this. So that they're both on carbons 1 and 5. Are there any questions on that one? No? Okay, on to the next one. So for number 4, we have a carboxylic acid. So carboxylic acid, when reacting with NH3 in heat, is going to turn it to an amide once again. So we're going to have another amide reaction. So we have our benzene ring, but this is going to become an O and then NH2. So we have another amide. And then for our second step, we have SOCl2. And for carboxylic acids, we know this to cause the carboxylic acid to become an acyl halide. But this SOCl2 is going to cause, whenever it's reacted with an amide, is going to cause it to become a nitrile group. So our next, the product of our next step is going to have this one carbon right here, but this nitrogen is going to be now not having any hydrogens, and the carbon isn't going to have any double bond to the oxygen. So it's going to become a C triple bond N. So we have our nitrile group with our SOCl2. Then our third step, LiLH4 and H2O, that's going to just protonate both of the carbon and the nitrogen. So our third step, we have CH2NH2. And this is going to be our primary amine, right? And so whenever we have a primary amine and our final step, sorry, for our final step, we have a ketone. And whenever we have a primary amine attacking a ketone with amine, that is going to form an imine. So IMINE. So our product for this is going to be this is going to have this this NH2 bond is going to be instead of having two hydrogen bonds, it's going to just create a double bond where this oxygen was. So this essentially this nitrogen is going to be replaced with the oxygen, or this oxygen is going to be replaced with the nitrogen. So we have our group CH2N, and then that's going to be double bonded to the C that the oxygen is attached to, CH3CH3. That's are there any questions on that one? All right, on to the next one. So on this one, we're going to use the ethylene diol. And so we know that because we have two different carbonyl groups. One of them is an aldehyde and the other is a ketone. So we know that aldehydes are going to be more reactive than ketones. So that's why it's going to be reacting with the aldehyde instead of the ketone. So our first step is going to be to use the diol /H+, and that is going to cause the it's going to be a protecting agent to protect the aldehyde group. So for our first step, we have this bonded to the O, and then this O is going to be replaced with that group, and then 1, 2, 3, 4, 1, 2, 3, 4, and then this is going to be our final structure for number 1. Then for number 2, we're going to use HCN to attack the ketone. So whenever we do this, it's just gonna attack the carbonyl carbon. And so for number 2, we have our OHCN and our protected aldehyde group. And for our final step is just to use H3O plus to get our aldehyde back, and that's going to give us the final product. Are there any questions? Yeah. Yeah, NaCN, but H plus. Yeah, with H plus. Yeah, let me actually. You can use HCN or NaCN /H plus. Yeah, that was a good question. Any other questions on this one? All right, on to the next one. So in this one, we have a beta keto ester. So NaOET ethanol. What this is going to do is this is going to cause the alpha carbon to be deprotonated. So this is going to give it a minus charge. So we have our group. Well, let me finish drawing and then draw the charge. So that's going to be the reaction for our first step. So our second step is going to attach the CH2Br with the not CH2Br, but the CH2 benzene to where this minus charge is. So for our second step, we have our the same thing, but this time we have instead of this minus charge, we have this benzyl group. So and then H3O plus 180. remember, if we look back into the facts section, this is decarboxylation. So if we look back at the facts section, if it would be decarboxylated at H3O plus at 180 degrees Celsius, this is pretty much the same concept. This is just saying that the ester would leave, right? So in this case, we cleave this bond right here, and so the ester leaves, and so that is all that would happen, and it would cause the final product to look like this. CH2, and then wait, okay, so that's a C, CH2, yeah. Then our benzene ring. Are there any questions on this one? Pretty straightforward. Okay, onto the mechanism. So on this mechanism, we kind of have a Grignard reaction, but we want it to create a ketone from the nitrile group. So first off, one thing to take note is that it's also asking us to create this NH3. So we're gonna have to eventually we're gonna have to take off this the nitrogen off the nitrile group, and we're also gonna have to create a ketone. So it's good to just take note of that. So we know for Grignard reagents that they're gonna attack the partially positive carbon. So this carbon is going to be attacked. That's going to cause this bond to go back to the nitrogen. And so for our first step, we're going to have the C double bond N, and that's going to be bonded to CH2CH3. And this N is going to have a minus charge. So I guess it can be stabilized with MgBr. So it's stabilized with MgBr. And so our second step, what we can use is H3O plus. Well, I guess not like this. But this nitrogen is gonna, because it has a minus charge and the second step is H3O plus, it's gonna attack the one of these hydrogens on this H3O plus, and that is going to stabilize the charge. So our next step is going to be C double bond N bonded to an H. Well, I guess I can just NH bonded to CH2CH2. So that's our next step. It's also going to be our third step, actually. So right now we don't have anything. So, but this nitrogen can take another. It's looking to take another hydrogen with its lone pair. So I'll just keep going down, I guess. So we go H. It's going to take this oxygen, or hydrogen, sorry. And then it's going to have C double bond NH2, and this is going to have a positive charge on it. And so now we can finally do some fun things. So because it has a plus charge on it now, what we can do is we can cause some resonance by having the H2O to this lone pair to attack the carbon, and that will move this double bond onto the nitrogen. It'll give the nitrogen a lone pair to stabilize it instead of having a double bond. So the product for that step is going to be like this: C bonded to an O, two hydrogens, NH2, and then CH2CH2. And now what we need to do is we need to deprotonate the oxygen because right now it's just H2O, so we can just use H2O one more time to take this hydrogen off. And the product for that, we would have this C and H2 OH CH2 CH2 3. CH2, CH3. I've been writing CH2, CH2 this entire time. That's crazy. My bad, guys. Alright, and then moving on. We're gonna have this lone pair on the nitrogen. Because we want the NH3 to be formed, we're gonna have this lone pair attack an H3O. So this is going to attack that, break that bond, give us the oxygen. So now we have finally this product, which is going to be our C12OH NH3 with the plus charge on it, and this CH2CH3. And now what we can use is resonance. So we know that oxygen has two lone pairs on it, and NH3 is a good leaving group. So what this is going to do is that this oxygen is going to create this double bond, and this bond with the NH3 is going to break. So the NH3 is going to want to leave. So the product for that step is going to look like this. We have the C double bond OH positive. Oh, that's crazy, actually. Did you guys see that? Oh, man. I'm on a timer. All right. No NH3. The NH3 is created. So NH3, I'm just going to circle that. And then what we're going to do is CH2CH3. And we have our positive charge on the OH. And so what we can do now, what we actually have to do, to get full credit, we need to show resonance. So we'll just put the positive charge onto the carbon. So just for like resonance, I guess. C plus, and then this is gonna have OH CH2CH3. So we have the two resonance contributors, and then our final step is just going to be to deprotonate the oxygen, so that we can have our final thing. So H2O is going to be perfect at that. So the H2O is going to have that, take that hydrogen off of the oxygen, and it's going to, it's going to take the hydrogen off of the oxygen. It's just going to create it into a ketone. So that is going to be our final product. Just C double bond O bind to CH2CH3, and we have created the NH3. Are there any questions on that? Yeah, I mean, you do have to only show the most stable contributor, but for this one, I think on the answer key she wanted to at least show like one resonance, I guess, but she wanted it to be for full credit. Yeah, I mean, it says that in the instructions as well, but I think for this one it was just a little bit different, just in case. Any other questions? All right. So onto the synthesis. So on this synthesis, we have an amine. And so the first step we want to do with an amine is that we want to create an amide. And the reason we want to do that, and the way we can do that, is by using a two-step reaction called LiAlH4 and H2O. And what that's going to do is that's going to cause this carbon to have a carboxyl group on it. So we have our benzene ring CH2CH2 double bond O bonded to the N with the CH2CH2 or CH2CH3 CH2CH3. So we have this structure now. And so what we can do here is that we can actually cleave this structure right at the center between the oxygen and the nitrogen, and we can have two separate structures. So now we can have this benzene group to be with the to have a chlorine on it, or chloride, not chlorine, plus the NH with the two groups on it. So we have an amine and we have an acyl chloride. So I'm gonna start with the amine first. So we can keep going down this way. Just LiLH4 H2O, same thing. I think you have to write it in 2 steps, not how I just wrote it. H2O, and that's gonna do the same thing one more time. And then if we just cleave that, we have the OCl like this, plus the NH2 CH2 CH3. And I'll go by this one more time. We'll just do it's kind of like Grignard, I guess, but it's just like repetitive, but it's okay. NH2O, and then whenever we just cleave that, we have NH3 plus the O, and then that's bonded to C, to this Cl. And so we have this OCl structure like over here, so I'm just gonna put the arrow over here like this, and I'll just synthesize it from here. So from this acyl chloride, wow, really drawing arrows the wrong way is crazy. So we can use SOCl2, and that's gonna reduce it back down with carboxylic acid. And our final step, what we can do is we can just use Jones or sodium dichromate. So I prefer Jones because I don't like writing out the entire thing for sodium dichromate. We can just synthesize that that carboxylic acid from a primary alcohol, OH. And if we look at the top, we want to make it from alcohols or alkenes of 2 carbons or less. And if we look, we have 2 carbons and the alcohol. So this is a valid starting material. And so now that we've done the hard part, we can go back to the easy part. This one, again, we can use SOCl2. And this is going to create a carboxylic acid. So this carboxylic acid, what we can do is we can use the same Jones again, and this is going to cause it to become a alcohol one more time, and OH like this. And so on this one, what we can do is that we can cleave it over here and have do the Grignard reagent 2 times. Or we can cleave it over here and have the Grignard reagent react with an epoxide, which would be a lot simpler. So that's what I'm going to do right here. So we're going to have this like this. We're going to have the Grignard reagent. Make sure whenever you're doing Grignard, you do H3O plus, like over the arrow. So we wrote H3O plus over the arrow. We have the Grignard reagents plus the epoxide. To get the epoxide from the alkene, we can just use MCPBA. And so that'll be our 2 alkene. Then we have our Mg/ether. This is going to be Br now. And to put Br into a benzene ring, we can use Br2FeBr3. And then that is just going to give us our benzene starting product. So that is the synthesis. Are there any questions on that one? No questions? Okay. Let's see what better we're working with. We still have 8%. We're chilling. Okay. So on to the last spectroscopy. So for this spectroscopy, we have the compound C7H12O2. So if we calculate the unsaturation number, this is going to be equal to 14 minus 12 plus 2 over 2. That's going to give us an unsaturation number of 2. So we have 2 double bonds in this structure. So if we look at the spectroscopy, if we just look over here, we have this peak over here, and this is going to give us the C double bond O. This is going to be a C double bond O peak. So we know we have a probably either a ketone, probably not an alcohol, because usually for alcohol we would have like a very big peak, very broad peak over here, but we don't have that. So we don't have that, so it's going to be just right. It's just going to be either a ketone from what we can tell. And now if we look over here, one thing I noticed like straight off, so weird, wait. One thing I noticed straight off is that there are 3 hydrogens right here from the 5 to 7 range. And this is going to be the 5 to 7 range for the alkene hydrogens. So these are alkene hydrogens. So we know that there's going to be a C double bond O, but we also know there's going to be a C double bond C. And what this tells us is that there are going to be 3 alkene hydrogens. So this C double bond C is going to have 3 hydrogens attached to it. So there's going to be at least 1 carbon with there's going to be at least 1 carbon with 2 hydrogens, and the other carbon is going to have 1 hydrogen, which means it's only going to be 1 sub on the alkene, which is good to know. So we have an R group right here. Now if we look at the rest of this, we have a CH3 right here. So this CH3 is going to be bonded to a CH2. Then we have this CH2 2H multiplets, with these multiplets right here. So it's fine. And then we have over here a downfield CH2, which is bonded to CH2. So this is going to be slightly downfield, so it's probably bonded to an oxygen as well. So because we have this, what we can also do is look at the carbon-13 NMR. And if we look over here, this peak, if we look over here, we have 160 to 185. And this is going to be in the range, and this is going to tell us that it's going to be a carboxylic acid or an ester. So we know it's not going to be a carboxylic acid because this has the O right here. So it's probably going to be an ester. So to put it together, we know we have like an ester that's going to be formed like this, the carbon right here, and then this is going to be O-CH2 CH2, and then something along those lines from this peak. And then we also know that if it was going to be coming off this way, if there's like a CH2 right here, there would probably be a 2H. There would probably be 2 H's looking at 0, right? So that would tell us that there was there would probably be a 2H peak somewhere around here, which would have which would just be a singlet, right? Because it's looking at no hydrogens, right? So because there's none of that, there's not a singlet there for that. What happened? Okay, yeah, my eraser keeps disappearing. Sorry. Because there's no hydrogens there, or because there's no singlet there, we know that this this is actually bonded straight to the alkene carbon, like this, right? So this is like part of the substituents. So if we go for our final product, we have our 2, and then we have our carbon, which is bonded to the ester, and then we know that we have a 7 carbon chain. So if we look right now, we only have 3 carbons. So if we need 4 more carbons to come off of this oxygen. And so right now we only have a confirmed 2, and then we know there's a CH2 CH3 that is not downfield at all, right? So if we just write this CH2 CH2, and we know we have the one place for the CH2 CH3. This, if we connect these two, we know that we have the multiplet that was unexplained, but this would make sense to have a multiplet because we have so many CH2s in a row, right? And it's not as downfield. So this multiplet that we have is explained by this butyl chain coming off of the ester group. So that would be our final product for the spectroscopy. Yes. That the ester was connected to what?
Obviously like two O's,
Mm-hmm.
and there's no carboxylic acid, but
Right.
sometimes like there will be like a C, like a carbon, then the ether. If that makes sense.
Okay, yeah, I know what you're saying. So the reason we know it's not that is because we have this peak right here, and this peak tells us that it's going to be a carboxylic, or not a carboxylic acid. It's going to be a carboxylic acid or an ester. So because of that, we know that it's going to be a double bond, and then the O, like double bond O and then O. That makes sense. If you're asking, oh sorry, I think maybe you were asking if it was like this, if it was bonded like this. Is that what you're asking?
That makes sense.
Yeah. Uh-huh.
Are they typically going to be the 6 to like 6.5, 7?
Yeah, they would be around the 5 to 7 range. And if we look at this, sorry, I was supposed I wanted to go over it as well. If we look at like all of the hydrogens, all of these hydrogens are unique. So if we look at one of these hydrogens, this hydrogen would be looking at a 1+1 and then another 1+1. So it would have 4 peaks, and so that's explained by this one right here. This hydrogen would look at the 1+1 only, 1+1 and another 1+1. So we would have another 4 peak. Technically, I guess we don't. Whoa, that's strange actually. Oh wait, no, wait. These are technically the same hydrogen. No, they're not. I lied. I'm tripping. But there would be I think it should have 4 peaks. This hydrogen should have 4 peaks. Then.
So it'll split with the one that it's connected to.
Mhm.
The same alkyl split hydrogens on the same alkyl split themselves. But then its neighbor is going to be blocked.
Oh yes. Oh, you're right. You're completely right. Yeah, this neighbor is gonna be it's gonna be connected to no carbons right here. That's why it's showing the doublet. I see what you're saying. Right. So on this side it has no carbon, so it's gonna be just the doublet, and then also on this side from right here, it only has one neighbor, and then this one. So this is also gonna be just a doublet. So that's why we have the doublet, quadruplet doublet. Yeah. One more time. A dye substitute. Hmm. Oh, okay. Yeah. Like if it was dye substitute, I understand what you're saying. So if it was dye, it would probably only have, first off, it would probably only have like 2 of these peaks, right? And then depending on how it was substituted, if it was substituted like this, then maybe this peak would have like this hydrogen, like 1H would have just a 0+1 peak, so just a singlet, and this one will also have a singlet, so there would be like 1H singlets. Or if we had them on the same side, say like say if these were hydrogens, then we would have a 2 plus 1 peak. So one of the both of the hydrogens would have 2 plus 1 peaks. Does that make sense? Or 1 plus 1 peak, so double it. Yeah. Okay, no worries. All right. Thank you for coming. That's going to be the end of the exam review. If you have any questions, you can come up. But yeah, good luck on your exam.